Hello everyone. Today, we'll dive into the fascinating world of the Cauchy Functional Equation and explore what makes additive functions tick. Last time we played with functional equations where shifting or doubling the input completely pinned the function down.
So now we want to understand, in general, how an additive rule can determine a function.
Previously, we discussed functional equations for g, used ideas, periodicity, scaling, fixed points. Theme: structure forced by simple rules. Keep that theme in mind. Our simple-looking additive law will turn out to be either very rigid or extremely wild, depending on tiny extra assumptions. Here's the single equation that will drive our whole story today. This formula says that the value of f at x plus y equals the value at x plus the value at y. That is exactly what it means for f to be additive.
So any function that treats addition perfectly, in this sense, is a solution of the equation.
It's a simple-looking rule for the function f. In a nice world, we have straight lines described by f of x equals k times x. In a strange world, we encounter wildly irregular additive functions f. The puzzle is that this one innocent-looking rule produces both familiar straight lines and unspeakably wild functions, and we will see what separates the two worlds. Let us now state the Cauchy functional equation carefully, the way an analyst would.
I want to see exactly what we are assuming about this mysterious function, f.
The equation says that for every pair of real numbers x and y, applying f after adding is the same as adding after applying f. There are no other hidden conditions yet. Unknown function f from real numbers to real numbers. The equation holds for every real pair of x and y. It expresses the pure additivity of f. We seek all such functions f. Before chasing deep results, we should squeeze out the easy consequences of additivity. From the additive rule, you quickly get that f sends 0 to 0, flips signs correctly for negatives, and respects integer multiples.
So, at least for integer inputs, f is already behaving exactly like a linear function would.
Plug 0 into the equation f of x plus y equals f of x plus f of y. Use x plus negative x equals 0 to find the negatives. Add x to itself n times. These simple properties are the first hint that our solutions are strongly constrained, at least along the integers. The classic Cauchy argument now pushes this integer behavior out to all rational numbers.
So we want to show that every rational multiple of a point is forced to lie on one straight line.
Using additivity, you show that dividing x into q equal pieces divides the value of f by q as well. So rational multiples behave exactly like a straight line with slope f of 1. From integer scaling to rational scaling, take x and divide it into q equal pieces. Set x equal to 1 so f of 1 controls all rationals. All rational points lie on a single line with slope k. Now comes the beautiful part. A tiny regularity assumption upgrades rational linearity to full linearity on the real line.
So continuity is the magic ingredient that fills in all the irrational gaps between rational points.
Since we already know f of r equals k times r for every rational r, continuity and the density of rationals force every real x to land on the same straight line. Already, f of r equals k times r for rational r. Assume f is continuous at 0 or at 1 point. Additivity spreads that continuity to all x. The density of the rational numbers pushes the line through every real x. Here is a less famous but very powerful twist. You do not even need to assume continuity directly.
You are saying that just being bounded on some small interval already forces the function to be linear everywhere.
Additivity lets you propagate that small bounded interval all over the real line, which ends up forcing f to be continuous and therefore linear. Assume that f is additive and bounded on the interval from a to b. Use the additivity to bound f at many other points. Demonstrate that f is continuous at 0. Then f of x equals k times x for all real x, Analysis gives another beautiful condition. Measurability also forces linearity.
So, as long as f behaves well with respect to the idea of length or area, it cannot be one of the wild monsters.
Measurability rules out the kind of wild sets you need to build a pathological additive function, so the only survivors are the straight line solutions. The function f is measurable, meaning it works well with length and area. Includes polynomials, exponentials, trig functions, etc. Measurability plus additivity rules out wild jumps. Once again, only the straight line solutions of f of x equals k times x remain viable. Now for the shocking twist. If you drop all those regularity assumptions, the story changes completely.
So the same equation can have solutions that are nothing like a straight line at all.
With just additivity, many strange functions appear. Not continuous anywhere. Unbounded on every interval. Not measurable. Clashes with length and probability. These monster solutions cannot be written by any reasonable formula. They are more like a bizarre assignment of values to points that still happens to respect addition. Let us very briefly peek behind the curtain at how one might build such a monster, without going into full technical detail.
I am curious about the idea, even if I do not see all the set theory behind it.
View the real numbers as a vector space over the rational numbers. Choose basis elements b sub I using the axiom of choice. Define f of b sub I arbitrarily on each basis element. Extend f to all x using rational linearity. The key point is that additivity only cares about rational linear combinations. So once you choose values on a basis, every other value is forced, and most choices give you a wildly discontinuous function. Let us step back and organize what the Cauchy equation has taught us.
It feels like the moral is that additivity plus any reasonable regularity completely locks down the function.
Cauchy equation capture pure additivity. All reasonable solutions are f of x equals k times x. Extra conditions like continuity or measurability matter. Functional equations like this are not just contest puzzles. They reveal how imposing a tiny bit of structure can turn chaos into a perfectly straight line. Let us connect this back to the fixed point functional equation we studied earlier.
Right. That was the one with a periodic rule and a doubling rule for another function g.
These equations encoded periodicity and scaling for g, and together they secretly forced g to behave like a very rigid additive function. Periodicity condition on g, scaling condition on g. Together forced g to be constant. Same philosophy. Additivity plus control gives rigidity. We have explored the additive Cauchy equation. The natural next stop is its multiplicative cousin.
You mean the equation where adding inputs multiplies outputs, which should connect to exponentials.
This exponential Cauchy equation describes functions where addition in the input space turns into multiplication in the output space, which is the hallmark of exponential behavior. Additive Cauchy equation, foundation of linearity. Next, mix additivity with multiplicativity. Exponential Cauchy equation, f of x plus y equals f of x times f of y. Vote in the comments for related topics. Before we wrap up, try one concrete problem that uses everything we have learned. Because f is additive and continuous, our earlier theorem says f must be a straight line k times x, and the value at 1 being 3 tells us that k equals 3. So f of x is 3 times x.
So the answer is f of x equals 3x. And the real work was noticing we could invoke the general Cauchy result instead of starting from scratch.
Practice. Find an additive function f where f of 1 equals 3 and it is continuous. Determine f of x. Reflection. Which regularity condition surprised you most? If you can explain out loud why this problem forces a linear solution, you have really internalized the Cauchy equation. Post your solution and reflections, and let me know if you want to dive into the exponential version next. Thanks for watching this. Subscribe to Thinking in Math for more topics. We welcome your feedback, leave questions and suggestions in the comments.